Okay. So you execute first this vector add.cu program, profile it, so throw the output in this name, and then you have to open this remote desktop. Once you open it, can you confirm, just raise your hands, how many of you are able to open this remote desktop? Okay, fine. Most of you are able to open it. Okay. Now click on this NVIDIA Insight Systems. It will give you this environment, and you can go to File and Open, and you can click on this vector add no prefetch report, right? If you don't compile this, execute these two cells or run these two cells, that file will not appear here. So if in your case, if it is not visible here, then make sure to execute these two cells, only then it will be visible here, right? Now what we are doing, whatever ANSYS profile result that we observed here, right? We are storing into a new format with output file name vector add no prefetch report, right? So this is a QDREF file, right? So it is referred as QDREP, that is the extension of that file. So this file can be given input to this visual profiler, and once you open it, it will give you all the details in visual format, right? So whatever errors and warnings are there, you just ignore it, right? And this is nothing but your visual profiler. Now visually you are observing what is happening throughout your code execution, right? So out of which you close these threads and everything, and you can expand this CUDA, and you'll see all these details here, right? So you can see here in this line kernels is there. If you want, you can zoom in little bit. Right? So either you can create a window here and right click and zoom in, or maybe you can just click on this zoom button, right? So you can see here during this add vectors into kernel is there, and during that time we're having some red spots here, right? If you take your cursor on that, it will show you the message that CUDA memory operation in progress. There are page faults occurred, and the data is transferring from host to device during that kernel execution, right? And if you see here, these page faults are occurring during the kernel execution or that GPU function execution. You can see here the blue color indicates here, if you click on this add vectors into kernel is executing, right? And during that execution, you can see here memory transfer is also there. In unified memory section, you can see some red spots are there here, right? So there's those red spots are indicating while your kernel is execution is happening, your data is being transferred, right? If you go on this add vectors into kernel, you'll see all the details about that kernel, right? How, at what time it is started, at what time it end, how much time it is consumed, then what was the grid size, block size, right? So all the details you'll get in this if when once you take your mouse cursor on that particular function, right? Now this way we can observe. Now you can go back and to check your code what is happening here. So you can see here before this add vectors into kernel, data for A, B, C was residing on the CPU memory because these init with functions are called from the CPU side. Now this ABC is present on CPU side, and then we are calling this add vectors into, and that's why you'll see while this function is getting executed, right? So all the data related to A, B, and C vectors is transferred from CPU to GPU, right? You can see check here. it is showing CUDA memory operation in progress, host to device transfer. Okay, and it is giving also how much time we are spending on data transfer, this, right? And red color, it is indicating that page faults are occurring here. Fine. Then next to that, we have again here page faults are occurring after your kernel execution also. You can see page faults are occurring, and here the page faults are occurring because your validation code or check elements or code is after your GPU execution and is expecting this C array, right? So while executing this check elements array, then it is going to perform data transfer from device to host. So if you go and check here, it will show the message that device to host data transfer is there. Migration cause is because of page faults. Fine. So this is how we can also visualize your profiling results using this NVIDIA Visual Profiler, right? So again, here we are working on very small assignment. So that's why you may think that it is unnecessary, because it is very clear that once by looking at program itself, you can take whether page fault is occurring or not, right? Now you can imagine, let's say you're working on very big project where maybe hundreds of files are there, or maybe hundreds of functions, different functions are there, and you're calling these all functions throughout your execution, and we are having maybe hundreds of GPU functions and plus CPU functions. Then it is difficult to, you can say, figure out just by looking at your code where actually the page faults are happening and where actually data is transferring from CPU to GPU or vice versa, right? So in that case, you can just profile your entire code, and you can use this visual profiler to check where actually data transfer is happening, right? Or maybe based on that, you can decide strategy. Like in previous assignment, we decided to convert this init with function as a GPU function, so that there will be no data transfer, right? Okay, so again, you go through this visualization, you zoom in, zoom out, and get familiar with this environment, right? I'll give a few minutes to do that, and then we'll continue with the next topic. Okay, I guess all of you are familiar with this environment now. Now, same code will be using here prefetch instruction, right? So before we directly call this add vectors into function, we'll be transferring data from CPU to GPU, right? Using this CUDA mem prefetch async function, right? So why we are using this CUDA mem prefetch async? Because if you don't do this, then during this kernel execution itself, it will show you that data transfer or page faults, right? So you can see on timeline we are having vectors add into this kernel is there, and during that kernel execution itself we'll be having these page faults, right? And page faults means we have to transfer that page from host to device or device to host, right? And that also considered inside your kernel execution time, right? So if you don't use this prefetch asynchronous prefetch, if you use prefetch, you can see here while the kernel is executing, there are no page faults are there. Already data transferred using this use prefetch from host to device, right? So that's why you can see here we are using this prefetch async. So the data will be transferred in only one chunk, right, without making some pages, right? So this will save your also time while converting into pages and maintaining the page tables and all those things, right? And that is visible here in case of your visual profiler also. Fine. So the purpose of this visual profiler is to just observe the execution of your program visually. Okay, got the difference with prefetch and without prefetch, how it is going to look different in your visual profiler? Now we have this another version of that add vectors program where we initialized data on GPU only, right, using the init with functions, right? Now let's try to see how it looks in case of your visual profiler. So obviously we are not expecting to have page faults because the kernels are getting initialization is happening on GPU itself. So only we'll observe those page faults when we are executing these check elements. That means after your add vectors into, right? So in visual profiler also we are expecting those red spots after your add vectors into kernel. So again you execute these two cells for this init kernel solution and then go back again. It may ask you multiple times password. We go back and again open. We'll see third one is first one is init kernel report, right? And you can see here you just minimize the thread section and expand CUDA section. Expand memory, expand context and kernels. Right now what we are expecting, there are two kernels, init with kernel and add vectors into kernel. So init with there are three kernels and add vectors into only one kernel. So you just select this region, right click on that and zoom into the selection, right? So you can see here we'll be having these many kernels. So three init kernels and one add vectors into kernel, right? And you can observe here the page faults are happening after execution of this add vectors into kernel. Fine. So before that there are no page faults. You can see here before that there are no page faults, right? So after that only we are having these page faults. Okay. Yes, you just expand if you want to see all those things in detail here, right? So again, the same thing, whatever we have observed in your command line profiler in terms of some information, here we are getting the complete timeline at what instance, which particular activity is going on, whether it is data transfer from host to device or device to host, or what is there are page faults are occurring or not, which particular kernel is currently getting executed, right? So all those details we can get in this visual profiler. Fine. I hope everybody can open these remote desktop and practice it. Now the fourth version is we'll be having asynchronous prefetch back to the host also, right? So right now we are observing these page faults here. Now let's see if you prefetch back to host, then whether we'll get uh, page faults or not. So obviously here we are not supposed to get any page fault. So let's again compile and generate QDref file, right? And again go back, you open, and there will be one more file. No prefetch host report, prefetch to host report. You open that, and we'll again do the same thing. Minimize thread section, expand CUDA section, expand memory, and you can see there are no more page faults, right? Right, you can see there are no page faults after your this GPU add vectors into function, right? But if you compare this init with, you'll see there are some page faults after add vectors into prefetch also. You'll see there are some page faults after, right? Because prefetch to host, when you are using, there are no page faults when you go for this uh, CUDA mem prefetch to CPU side, right? So same things, only we are visualizing here. Take few minutes, play around with. You just try to observe each and every section in that visual file. Okay, so now let's continue with the final topic from this CUDA C C++ certification, that is CUDA streams, and after that you'll be having immediately your coding assignment, right? Final exercise problem, n-body simulation. Again, you just have to modify that code. You don't have to write code from scratch, right? You just have to modify this code so that it will be executed on GPU side, and you don't have to use any advanced concepts. You just stick to the topics that we discussed in the first two chapters, right? Chapter 1 and chapter 2. The knowledge of chapter and chapter. Okay, I think the connection was lost. So this is the last topic that is remained from your CUDA C++ certification, that is CUDA streams, right? Once we complete this, then we can directly jump to the assignment. That is n-body simulation assignment is there. All the instructions are mentioned. I'll explain it to you. You just have to modify this code, right? And once modified, so that it will be getting executed on GPU, and after that you just have to execute all those cells, and if your submission is correct, then you can go back to this page and you are supposed to assess, and once you click assess and if your submission is correct, then you will get pass message, right? Like this. So in my account it is mentioning that it is passed. Perhaps in your account it won't show any message, right? On passing this certificate, we'll get a certificate, digital certificate immediately, okay, that you can submit to us. Fine, so let's first complete that CUDA streams topic, and then we'll go for this assignment. So this is the last topic from your CUDA C++ certification. Okay, so as of now, we try to execute one kernel at a time. That is one GPU function at a time, right? So whether it is add vectors function is there, right? So with our initialization functions were there. So we tried to launch one kernel at a time or one GPU function at a time, right? For example, if you refer this code, so you can see here you are launching four kernels here, right? Three initialization kernels and one add vectors into kernel. Now what happens? All these kernels will get executed one by one, right? So if you recall, this we will call this init with function to initialize variable a. Then after that CPU will execute next kernel, then next kernel, and so on, right? So all these kernels CPU will launch, but on GPU side only one kernel at a time get executed, right? So that's the reason once CPU launch this kernel, it will not wait for this particular function to complete or GPU function to complete. It will immediately launch next, third, and fourth also. But on GPU side, it will be placed in one queue, right? In queue means GPU side, it will be having one queue like structure where init with kernel will be the first init with kernel will be there, second one, third one, and finally this vectors into kernel, that is fourth kernel, right? CPU will launch these kernels and CPU move to the next statement, that is whatever is there error or what is statement is there next to that, it CPU will continue to execute. But here we are using CUDA device synchronize, so CPU will stop here. Now on GPU side, it will execute one kernel at a time, right? So it will execute first init with kernel. Once it finishes, then it will go for the next kernel, next, next, right? This kernel execution will happen in sequential manner on GPU side, right? So this CUDA streams idea is like that. What if we can launch all these kernels at a time? That means, let's say three initialization kernels are there, we can launch at the same time rather than one kernel at a time. I will consider these three initialization kernels, I will launch at the same time, right? So obviously every init with kernel is parallelized, right? It will execute in parallel. Plus on top of it, what we are asking, these three kernels also will execute in parallel. Inside that there is also parallelism, and between these kernels also there is parallelism here, right? So whole idea of this CUDA streams is to launch multiple kernels in parallel, plus we can also overlap data transfer plus this kernel execution, right? So let's see this presentation now. So whenever you launch any kernel, that will be placed into a default stream, right? Or we can consider it as a queue. For example, let's say you are launching one kernel after another, then it will be placed in the queue like this, right? Instead of calling it as queue, we are calling it as a stream because we are having some stream of kernels. So all these kernels will be placed into this default stream, and on GPU it will get executed one by one in sequence, right? Now here by default all the kernel launch will be placed into this default stream, right? And condition is that any stream including default and instruction in it, here we are having kernel launch, must complete before next begin. So meaning is that we can launch kernel 2 or we can execute kernel 2 only if kernel 1 is finished. We can execute kernel 3 only if kernel 2 is finished. Similarly, we can execute kernel 5 only if all these kernels are executed from 1 to 4, right? So whatever instructions we are putting in this stream, those will be executed in sequence, right? But now this is the default stream. We can have one more stream that is called as non-default stream. And what is the criteria now? Here we can have multiple non-default stream. So whatever kernels are there inside your any default or non-default stream, they will be executed in order, right? So if I am having this kernel 1 and kernel 2 that belongs to stream 1, right, then kernel 1 execute first, then only kernel 2 can start execution. But if you are having, let's say, kernel 3 that is in non-default stream, right? So meaning is that we are having two kernels 1 and 2 in default stream 1, non-default stream 1, and kernel 3 in the non-default stream 2. Now here we can overlap their execution. So kernel 3 can parallelly executed with kernel 1 or 2, but kernel 1 and kernel 2 cannot be executed in parallel because they belong to same stream here, right? So point is kernels in different non-default stream can interact concurrently or can be executed concurrently. Kernels in the same stream, whether it is default or non-default, they will execute in order, right? So in this case, default stream 1, non-default stream 1, kernel 1 execute first, then kernel 2. Fine. Next statement is, here we are having again kernel number 4. Here kernel number 4 can be executed in parallel with kernel number 2 or kernel number 1. But in case of this non-default stream 2, kernel 4 can start execution only if kernel 3 completes, right? So parallel execution is allowed only with non-default streams, that is that too in the different streams, right? Then we are having kernel 5 here, then kernel 6, so they can execute in parallel. Now the default stream is special. It blocks all kernels in all the streams. For example, let's say we are having kernel 1 and kernel 2 here, this scenario. Now let's say you want to execute any kernel or any operation in default stream, then it will block all the remaining streams. That means you cannot execute any kernel or any operation in parallel with the default stream operations, right? So during that time you cannot launch anything, or it will not allow to execute anything in parallel with this default stream. And once it completes, again we can have parallel execution, right? So during kernel 5 execution, no stream is executing any operation, right? So default stream is blocking behavior. It will block all kernels in all other streams. Fine. So point here is, first of all, stream is nothing but a queue where all the operations will be placed that will be executed on GPU side, right? And all the operations in one stream are executed in order, right? The execution can be allowed in concurrent fashion only in non-default streams, and that too in different streams, right? And last statement is whenever there is an operation we are executing in default stream, it will block rest of the streams, right? So we cannot have anything that is parallelly executing in this default stream, right? So that is the behavior of this CUDA streams. Now this will help us to launch multiple kernels at the same time. And what is the syntax? First of all, we have to create streams, right? So non-default streams we have to create, right? Then we will utilize it and we'll try to understand how to destroy it, right? So simple syntax is we have to use this data structure CUDA stream underscore t to create a stream, right? And we'll first of all assign name or variable name to that CUDA stream, and using this CUDA stream create function we'll pass that address of that particular variable, and here it will create a non-default stream here, right? And now while launching kernel you have to specify in which stream you want to pass that particular kernel. So for that reason we can see here there are two parameters here that you are already familiar with this kernel, that is number of blocks and number of threads per block. The third parameter is related to shared memory, that is not in the context of this session. We will discuss what is this shared memory in the Python course, right? This will help you to improve the performance of your application even further, right? So we'll skip this part. What is third parameter, that will be discussed in the Python course. The fourth parameter is related to your stream, right? So meaning is that you created one stream here. Now you want to execute this kernel, some kernel in this particular stream. You can create stream 1, stream 2, stream 3 variables, and you can launch different kernels in different streams, right? Once your kernel execution is over in this particular stream, you're just going to destroy that stream, right? You created it, and after use you are going to destroy it. Fine. Now this is the useful technique to increase the performance even further, right? You can launch multiple kernels, but problem is that it is even possible that what if, let's say, you have written one kernel, right? And this is, let's say, in stream number 1 non-default stream, and this is non-default stream number 2. Now both these kernels can be executed in parallel, right? That is as per your stream concept. But what if, let's say, this particular kernel, that is number 1, is utilizing 100% CPU. That means it is requiring all the CPU resources, all GPU cores, right? It is exploiting 100% GPU. Then as per your CUDA stream behavior, kernel 1 and kernel 2 is supposed to execute in parallel. But problem is that kernel 1 itself is utilizing entire GPU. So in that case, what will happen? Though logically you are saying kernel 1 and kernel 2 execute in parallel, but kernel 2 get executed in parallel only if the required resources are available free, right? So it is not guaranteed always that the CUDA streams will ensure that two kernels will be executed in parallel every time. So it depends on resource availability, right? So don't consider that whenever you are launching multiple kernels, both will get executed in parallel, right? It is not provided that if your resources are free that are required by this kernel number 2, only then it will get executed. Otherwise, it will, though we are saying it is executed in parallel, but it will execute kernel number 1 first, then kernel number 2. Fine. So this is the behavior of your CUDA streams. Now let's try to understand using visual profiler here. So again, default stream behavior is there. So print numbers is a function. You can open that, sorry, program. Right. So what we are doing here, we are simply created one print number function, and it is printing the number, whatever number we are passing to that function, right? And inside the main function, we have written one for loop from I equal to 0 to 4, and we are inside that we are calling this print number GPU kernel, right? So 5 times we are calling this print number kernel, right? And every time it is going to print the message I, right? So first let's simply execute this. and see what is the output. So it is simply printing 0, 1, 2, 3, 4, 5. So 0 will be printed by one kernel, 1 will be printed by another kernel, and so on. Right? So 5 kernels we are launching in this for loop. Right? So what we'll do, let's create a output file, right, of this profiling, and we'll try to open in this visual profiler to see that behavior. Right? You close all these files that are previously opened, go to open, and you will see what is the name of that. Print numbers report. Yes, print numbers report. Close this threads section, open CUDA section. Kernels will be having, then zoom in, right? So you can see here we are launching 5 kernels or same kernel 5 times. So that's why you can see here on timeline there are 5 kernels displayed, right? So this is normal behavior or default stream behavior. Here we are not created any stream here. We just launching one particular kernel at a time, and that's why we can see here the print number function is executed one after another, right? Next thing is we'll try to use this concurrent CUDA streams, right? I will just open the solution. It is very simple to create, so I'll just copy paste simple program is there, and open this print numbers function program and paste here. Now what is happening here, in for loop you are creating a new stream, right? And the print number function you are calling in that particular stream. So every time you are creating a new stream and you are destroying it, creating a new stream and destroying it, right? And in every new stream you are trying to put a new or this put this print number kernel, right? So again save it, go execute it. Again output will be the same, but you try to run this profiling output now, right? And you go back to your visual profiler, open that file. The file name will be print numbers in streams. Open it, close this thread section, and open this streams. You will see there are 5 streams created here, right? So stream 13, 14, 15, 16, 17, right? Maybe the first 12 streams are dedicated for maybe other purpose, but here you can see every stream is having different number, right? Again zoom in little bit, right? So you can see here all the print kernel functions or GPU functions are kind of overlapped. So they are not getting executed one after another. They are completely overlapped here, right? So obviously why we want this overlapping, because just like your pipeline architecture, we are overlapping means we want to ensure that multiple kernels can be executed in parallel, provided that resources are available. So why to, let's say there are two functions, function 1 and function 2, but both of them are lightweight function. That means they are not going to utilize all the GPU resources. So in that case we can launch them in parallel so that overall time will be reduced, right? So this is the whole idea behind this streams. Getting it? Now the same thing we have to do, right, in case of this prefetch check solution. So here what it is expected, we want to use streams for concurrent data initialization, right? So here we are using we are creating three streams, stream 1, stream 2 and stream 3, and we will be launching these three initialization kernels for variable a, b and c into different streams, stream 1, stream 2 and stream 3. So initialization of a will be placed into stream 1, initialization of b will be placed into stream 2 and so on, right? So that's the only thing, and once you are done with, you can delete or destroy these streams. Fine, so that we can ensure that all these initialization functions will be executed in parallel. Fine, so you can execute and check its output also in the visual profiler. Fine, so this is all about your CUDA C++ certification theory, right, and the hands-on sessions. Now we have discussed all the things that are required to solve this next final exercise problem, that is acceleration of and optimize n-body simulator, right? So in this case, what is expected? First of all, you try to understand this code, and again, you don't have to understand what is the significance or meaning of this particular n-body simulator. You don't have to go behind the mathematics of that, right? If you want, you can check, but again, it is not at all required to go into the mathematical details. As a programmer, you just focus on what is mentioned in this particular code, right? What is expected from this, all the instructions are mentioned here. You just try to understand the entire program here first. It is a sequential program, it is given to you. Now some instructions are mentioned that you have to follow, right? You just assume some arrays are there, some structures are there, you just follow it, that's it, right? You don't have to go behind that, what is meaning of this body force function or what is meaning of n bodies, right? It is kind of galaxy simulation code is there, right? A very small portion of that code is there, right? That is n body simulation. Now coming to the point, what is expected here? This program is currently in CPU only form, that means it will get executed on CPU only, and it takes around 5 seconds to run 4096 particles, right? I don't know whether so this is a simple if you want to visualize what that particular code does, it is a three-dimensional simulation of your galaxy, right? So I'll just quickly forward it. Right, so this is the simulation that is happening. To simulate that, we'll be using that code. Right, I'll fast forward it. I'm just giving what is this n-body simulation. Even I also don't know what is the physics or mathematics behind it, right? So as a programmer, it is not required at all to understand what is significance of this code. It is just simulation. This code helps to simulate all the particles in the universe, right? Fine. So I think this much visualization is enough to get the motivation behind that assignment. Okay. So it is in three dimensions. So there'll be three-dimensional structures will be there that you are to supposed to uh, create. Okay. Now, so read the instructions carefully. So as of now, it takes 5 seconds to run 4096 particles, and it takes 20 minutes to run 65,000 particles. Now your task is to GPU accelerate the program, retaining the correctness of the simulation. First of all, whenever you are applying any parallelization, it is expected that your sequential and parallel output must be same, right? That means it is supposed to be valid output, right? So once your answer is correct, only your timing is you can say validated, right? So if your answers are correct and if time is let's say it is taking less amount of time, there is no meaning of that kind of solution, right? If your answer is wrong, then there is no point of reducing your time of your application. If your answer is correct, then only we can consider whether time is reduced or not. And this automatic evaluation is also going to do the same thing. First of all, it will check whether your parallel output results are correct or not. If your parallel output results are not correct, you will not get full marks for that assignment. Fine. Now, this is the guidance for your assignment. First, first effectors logic of the application, the body force function, right? So here we'll be having a body force function. They are asking us to make the parallel version of this function first, right? So what will be your strategy first? First, use global keyword here, then try to decide number of threads and number of blocks, and then body force function is supposed to be passed with threads and block configuration, right? So threads and block configuration you can mention here. Where is body first function called? Yes, here, right? So you can convert into your GPU function, and then you can go inside and you can modify this code so that it will be executed on a single on GPU using those threads, right? Then it is also mentioned that you are not supposed to touch any of the these codes that are mentioned here, right? This assessment will pass hidden initialization values to check the correctness. You should not make any changes to these files or else assignment will not work, right? So whatever it is mentioned in this main function till this point, right, you are not supposed to change, right, till line number 65, right? Let it be as it is. You just start focusing on whatever it is mentioned. For example, uh, here they are asking you will likely wish to refactor the work being done in body force function, right? You first focus on that. Maybe after that you can also parallelize this for loop, right? So again, and for this for this particular assignment, don't go and try to use streams and all those advanced concepts from the start. First, without stream you try to accelerate it. If it is possible, then only you can use the stream concept, right? The code base contains for loop inside main for integrating interbody forces calculated by body force, right? And this integration both needs to occur body force run needs complete before next call to the body force. So keep this in mind that choosing how and where to parallelize. So don't directly rush and try to parallelize this loop itself, right? Don't try to parallelize this loop. So you have to just make sure that you have to parallelize from this function. And it is mentioned that once this particular body force complete in iteration number 0, then only you can execute iteration number 1 body force, right? So that is a statement. So you can find out why they are mentioning this, right? Either you can use profile driven iterative approach, or maybe as per your convenience you can use. Now you're not required to add error handling to your code, right? As of now, you don't work on this error handling code also. You just follow, try to convert this body force into your parallel code. That's it. Okay. And after that, once you're done, you just execute all these statements here, right? It will run assignments. And after running assignment, it will display a message that whether it is successful or not. You're getting all the criteria satisfied or not, right? Maybe during, let's say, updation on all this working on this assignment, you accidentally closed or maybe accidentally deleted some portion of the code and you are not able to recover cover it. Then you can go back, right? You close the instance and restart it, and you can still work on that assignment. Fine. Now you can see already those reports and everything is generated. If I run this, so it is saying that application should run faster than 0.9 second. Your application is not yet fast enough, right? Because I have not updated anything, so that's why it is showing your application is not fast enough. But after successful modifications, it will display message that it is running fast enough, so that you can go back. Once you're executing this final statement, run assessment, you can go back to your home page and you can assess task here, right? It will give you grading after your evaluating your assignment or submission. Fine. And after grading, if you will get full marks, then it will display that message. Otherwise, it will mention pass or failed here. Right. So it is saying that it doesn't look like that you have completed the assessment yet. Please make you have completed the n-body assignment section 3 notebook. Then come back and try again. Now you can say here it is showing me failed because I have not modified this code. Fine. So you go and try to attempt all this. Try to use all this concept to solve this assignment. The simple clue is don't directly go for the streaming. You just use whatever you have studied from the chapter number 1 and 2. Fine. Any doubt in this case? And once you complete, get the certificate, uh, you are supposed to submit on uh, mail ID that I will provide all the details. And at the end of this section, you can see that progress also, right? What is your current progress? And can anyone show me your uh, course view? Because in my course, the feedback survey will not be there. So I'll stop sharing. One of you, please uh, share your screen. Anyone who is on the chapter number 3. Can anyone share your screen? Vinayak, are you there?
Yes, sir.
Share your screen.
Yes, sir.
Go to that NVIDIA page, previous page. Uh, yes, course survey is there. Go to next page on course survey. Yeah, so you have to submit all these, check all these boxes, right? And you have to share the screenshot of this to mail ID that we are going to provide, right? So two things you have to submit from each participant or from each of your team member. First thing is certificate and for each participant, and second thing is the screenshot of your feedback, right, to that mail, right, for every participant, not only for one feedback per team, right? Only if you submit all those required things, then you will be eligible for the next round, right? Those who are opting for this CUDA C++ based track. Fine. I'll provide all the guidelines how you are supposed to submit. Okay. Fine. So with this, you can stop sharing the next screen. Now with this, we can conclude this first certification sessions, training sessions for this CUDA C++ programming. Now will give you enough time to complete this assignment, right? I don't think if you go through first and second chapter, it will take hardly, at max, it will take half an hour to complete that assessment, to pass that assessment. But still, if you are getting some problem, that means your concept from your first and second chapter are not much clear. So you can go back and read the topics from first and second chapter. You practice those assignments from chapter 1 and chapter 2. Also try for uh, advanced topic also, right? And then you can again reattempt for this final assignment, right? Those who get certificate, even then you are supposed to revise all your concept. You can explore the topics from internet, some advanced topics related to CUDA programming, or you can explore any book if you are having, right? You can practice all the remaining maybe any other assignments also, right? And you can be ready for the next round. So that, okay. So just completing. The deadline is I think in that say schedule or something where I have mentioned deadline, I think 13th of this June. Let me confirm. Yeah, till on 13th June till 12 p.m. you can submit, right? Certifications for CUDA C++ user, right? For Python users, maybe we can extend the deadline. Okay, so fine, because Python code we have not started yet, so it will be injustice for Python developers to get less time for submission, right? For C++ user, you will have time till 13th of this June, right? Till 12 p.m. you are supposed to submit. Okay, any other query? As of now, don't trust to submit or send mail to us. We'll give proper guideline how we are supposed to submit. Otherwise, it will be difficult for us to collect all the reports. So team wise, we are going to collect all these reports. Fine. So let's have 10 to 15 minutes break here. So meanwhile, we can start working on that also, right? After 10 minutes, after 15 minutes, we'll be back again. If you have any questions still, you can discuss, right? And after that, we will conclude today's sessions, right? Let's have a 15-minute break here. We'll join again around 2:50. Okay. So meanwhile, work on the assignment. If you have any problem, you can just note it down. And at 2:50, we'll join again and we'll try to clear your doubts. Fine.